So let's go to the third topic, titled 10BST1S Link Segment Evaluation, Interconnect versus Cable. This presentation will be delivered by Safal Sharma, technical lead at Molex, specializing in signal integrity and EMC, working closely with product design engineers to optimize performance and ensure compliance with industry standards. So the stage is yours.
Thanks. Oh, can you check this one? Yeah.
The next.
Okay.
The previous and the laser.
Thanks. Good morning, everyone. So I'm Safal from Molex, and today we are going to talk about 10BST1S and its link segment performance. So this is the agenda. We'll be talking about background, basically how different 10BST1S compared to the other automotive Ethernet network, and cable versus interconnect effects in 10BST1S, and one additional topic which is really interesting, how to simulate off-the-shelf multi-way connector in 10BST1S networks, and key takeaways. So if you see Ethernet in general, right, so the data rate, the speed is increasing almost every year, right? And same trend we are seeing in automotive Ethernet. We had 100 base T1 and then 1000 base T1 all the way up to 25G, right? But instead of focusing on maybe 50G, we are really going down the data rate and focusing on 10BST1S, which is really a low-speed network, and there is a reason for that, right? So if you see every, like modern vehicles and all, so the content is going up, and a lot of features are being added every year, right? We see a lot of tractions on that. For that, we already have 25G, 2.5G, 5G, 10G. But if you see maximum communication that happens between ECU, it don't need this level of bandwidth. This much bandwidth is not needed. It needs a very, like maybe less than 8 Mbps or 5 Mbps, right? So that's why almost all the modern vehicles are equipped with different network technologies. So we have automotive Ethernet, way up to 10G or even 25G, depends. And also we have a network infrastructure to support the lower data rate, EC to ECU communication, right? Typically, it's done with CAN, LIN, all these legacy protocols. Now, which is good, it works, but the problem is, let's say, somebody is speaking in language A and somebody is speaking in language B, right? So we need a translator to make the communication smooth. So same way happens here because of the gateway. So there is a gateway that actually, it does the work of a translator to manipulate the data from, in this case, CAN FD to the Ethernet. Now the problem with gateways are these are already everybody might be knowing. So this really needs a complex software, and let's say every new message is being added to the vehicle, or every new information is being fed into the system, then the software or code needs to be updated almost every time, right? So it little bit makes things complicated. But if you see the another architecture, that is Ethernet-centric architecture, so with the help of 10BST1S, it's all Ethernet-centric. So there is no need of gateway actually, and this is one of the biggest advantage of 10BST1S. And one of the biggest drawback of automotive Ethernet was it was all point-to-point. If you see 100 base, 1000 base, all the way up to 25G, it was all point-to-point communication, right? The bus topology or the bus architecture was not there. But that has been fulfilled by 10BST1S. Along with that, it supports up to 25-meter cabling, simple topology, and many things, which I don't want to go into all those details because already we have seen a lot of talks, lot of presentations on 10BST1S advantage and all. So we are actually focusing in this presentation, we'll be focusing mainly on the physical layer, the cable, and the interconnects. So 10BASE-T1S physical layer communication can be implemented basically in two ways. One is point-to-point, and one is bus topology, where we can, so where there are a number of middle nodes. It can be a simple wire with a stub, or it can be a three-way connection, like a Daisy chain. And you'll see 100 ohm terminations are there on the edge node. Now compared to CAN and other technologies, 10BASE-T1S is really sensitive to these terminations, like 100 ohm. If we have 120 ohm or 130 ohm, CAN might work, but 10BASE-T1S is really sensitive. And it's also sensitive to the cabling. So if the cabling is not good, if the way we are untwisting the cable, when we are connecting it to the connectors, right? All these things actually matters for 10BASE-T1S network, which anyways we'll be talking in the upcoming slide. So link segment basically consists of interconnects and cable, and we can validate the performance by capturing the S parameter. We can see different figure of magnitudes like return loss, insertion loss, mode conversion, and in time domain, I diagram and all those things. Now really the question today is, right, so now all these figure of merits which I'm talking right now as parameter, all these things, so who dictates those parameters, or who is the dominating factor in link segment, if you see, right? So I mean, whether in the link segment, right, whether it's a interconnect or cable, basically it's a transmission line, and transmission line tends to behave differently at different frequencies, right? So at megahertz frequency, the wavelength is actually very big. It's very large. And interconnects are really short. So let's say my wave is traveling on this interconnect. The instantaneous voltage and current doesn't change. The current travels quite smoothly. So since it's very small, it's smaller than lambda by 10, so the distributed effects of transmission line, like the RLGC distributed effects, is not significant. So the instantaneous impedance doesn't change. So it basically behaves like a short, so it doesn't have all those effects. But if you see the cable, it's longer than interconnects. It actually gives the distributed effects. So we have to see the instantaneous voltage and current changes with the position. The phase also changes of those wavelength. That's why the impedance matching, the way that we control the cable, untwist is very critical. And so we have two cases here. One is engineered 100 ohm control differential pair connector. So the pins are 100 ohm differential. And we have an off-the-shelf multi-way connector. So it is not differentially controlled. So the impedance is unknown. You can see from the 3DR. Now we did another study. We put both of these connector in a system with a cable, and the interconnect behaves like a transparent. If you see, this result at 700 picosecond. So it really, so the answer, what is critical? So it really, comes from this graph, right? So, and in the next one, what we did, now we know that the cable has more weight compared to interconnects in a link segment, right? So now, what about the untwist? So in the next slide, we did a lot of studies on cable untwisting. So the 70 mm was the worst case. Then from 50 mm coming all the way down to 10 mm. And then we will try to show how the budget looks like, what will happen to my return loss, what will happen to my mode conversion, and finally the EMI. Because obviously, like cable, even if you see a lot of presentations in this event, right, many speakers, they spoke about EMC. And EMC is, even though it's a low data, low speed system, EMC is always a challenge. Yeah, I mean, so return loss passes the budget. So this is the limit lines from TC9. So 70 mm is the worst case as expected because of the untwist. The reflections are more, right? So because of the impedance mismatch, return loss goes all the way, almost touching the limit lines, but it passes. But the interesting thing is maximum of my budget is being used here, right? But if you see the mode conversion, it actually fails. So 70, 50, 45 mm mode conversion is actually failing. Now, the intended signal in a differential pair is always a differential signal, but because of whatsoever reason, the common mode signal will always be there. But because of the excessive mode conversion, my common mode signal starts becoming more and differential becoming less. And common mode tends to give more EMC compared to differential because it's having the same phase. So the net electric field is addition of the electric field components. So compared to a differential signal, common mode tend to give more radiation. So having more common mode means the chances of EMC and EMI will be more. So we did some studies on to capture the radiated electric field strength. So we used dB unit in this graph. So basically, it tells that the more, if you see the graph, right, it's almost 85. The more voltage we have, the chances of emission and radiations are more. And at 75 untwist length, the radiated electric field strength is very huge compared to, let's say, 30, 25, 15. So the radiated electric field strength is decaying when we are, varying the untwist length of the cable. And same trend we saw in the mode conversion also. Now, in the next one, what we did, we injected a 1 volt plane wave into the system. We also measured what is coming in. So obviously, untwist length creates more radiation that is going out. But what will be injected into my system? So we also saw the same trend. So the noise or the induced voltage coming into my system was relatively more when my untwist length was 70 mm, and it was less at 10 mm. So as I said, in the second slide, right? So cabling is actually very, very, very critical. Now again, so having said that, so cabling dominates my budget, my link segment, but connector is also very critical. It's not that connector doesn't have an impact. For example, like this is one slide. I don't want to go details into this slide. So we have a booth, and we are actually demonstrating this technology. We have a booth, so we have these samples, we have these connectors, PCBs. So if anybody is interested, if not visited, please you can visit. So basically, what we are trying to show here is, right, so we told that cabling is critical, but so DC chain can happen in 2 ways, right? So one is we can sort on the PCB. In second case, we can sort on the plug cable side. Now both the technologies are reliable, both meet the spec, and both are proven technologies. But having said that, the dual wire at plug, especially with dual soldering or double soldering, has significant advantages. One first advantage is we'll be getting rid of the stuff, or the stuff will be very less. That itself makes my electrical performance good. And so in multi-drop topology, right, there will be a lot of drop nodes. And let's say one node is for a ADAS system, which is like a mission critical system, right? It cannot avoid to fail. So let's say my drop node is going to the ADAS system. If it fails, then the entire system might malfunction. Or let's say I have another ADAS system there. So that kind of problem would be overcome by doing a DC chain on the plug side. It ensures if any of the middle node fails, the continuity is maintained, the communication link is established. So that is one of the interesting and good advantage of doing a DC chain on the plug side. And also, if we do this with the engineered connector, there are a lot of advantages. First thing is, I can really control my untwist. So since it is not a cream, it is a soldering solution, I can take it very close to my plug. That is also one of the advantages. And another biggest advantage of having engineered connector is something we'll be talking in the next slide. So I just want to summarize what we have covered so far. So we told that in system level connector impact is minimal, and I mean the link segment performance is pretty much dominated by cable, and the 10-base-T1S is very sensitive to the way we have cabling, the way we have terminations and all, right, and the untwist creates high mode conversion and more EMI. And so we also spoke about the sorting. So sorting on the plug side has more advantage compared to the PCB side. And so before I go to the next slide, right, so now we are talking a lot on cabling, adopting 10-base-T1S. One of the interesting question would be, can 10-base-T1S leverage a legacy wiring? So this is something I want everybody to think. Once I go to my concluding part, then maybe I'll try to give some answer. But this is a very interesting question. We also had this question on the last year of the event, because we are talking about adopting 10-base-T1S, right? But really it can leverage the CAN-like wiring. If not, what needs to be done? What kind of connector we need? That is something very interesting question. Now in the next part, I'll be talking about, now let's say I have off-the-shelf multi-way connector. Like let's say I have 100 pins, 20 pins, lot of 10-base-T1S is stacked on a one big connector, like a bulk connector, and I want to simulate that, because obviously I have to know my budget, right? So there is a spec, there is a channel budget, there is a mated connector budget with a PCB, with a at least 60 cable. So we have budget from IEEE TC9. So obviously we have to simulate before we actually prototype and do all those testings, right? Because we can go back and do the redesigning. But how do you simulate that? Do we use a idle port, or we have to use something else? So the problem with this kind of off-the-shelf connector is that now we typically don't know the impedance, right? Now normally if you talk about the ports in any electromagnetic solver, we need a reference impedance for those ports. Now I don't know my impedance, so what will be my reference impedance? 50, 100, 200. It's actually, if my reference idle port is very easy to create. Even we can automate it, right? Write some Python code, automatically tool will create. But what will be my reference impedance? If my reference impedance is not correct, then my S parameter won't be correct. It might give some unwanted, S parameters might not be correct. It might show it's passing, or it might show it's failing, which might be different in a reality. Then the answer would be we have to use a non-idle port, which need not have, where we don't have to actually define a reference impedance. The port itself can calculate and tell us the impedance of that system. It comes with another drawback, which I'll be talking in the next slide. Now, if you see the way electromagnetic waves propagates, right? So in a confined space, so there are two behaviors. One is a propagation mode. Propagation mode in a sense, let's say I have a twisted pair. I have a port here, non-idle port here. So typically TEM wave actually starts propagating on those twisted pairs. So these are the propagation modes. There can be higher order modes as well, but those modes actually propagate. And normally if the frequency of those waves are larger than λ/2, all these propagation modes starts traveling. They actually carry the energy and power from the port to the system. Now there are other kind of ports, we call it non-propagation or evanescence port. So they don't actually travel. They'll just be there on the port and it will start decaying exponentially. So alpha, like the attenuation constant will be very high in this kind of modes. So that's why they decay, they don't propagate. Now let's say if my port is very short, like because of whatsoever reason, I didn't create my port properly, if my port is very short. Now the rule of thumb is the electric field should be very high on the port edge, and it has to be very low on the, sorry, it has to be very high in the port center, it has to be very low on the port edge. This is a rule of thumb. If my port is really small, the electric field will be very strong on the port edges. And the strong fringing field would be there on the ports. So obviously the non-propagating mode, they don't get a chance to decay naturally, even though alpha is very less, they get reflected back to the system. We'll see sometimes the resonance coming in my S parameter, or we'll see high mode conversion, which in reality might not be there. This is one of the problem with creating a very short port. Another problem is especially in 10BASE-T1S. So we'll be having, let's say, 300 pins or 200 pins, right? Sometimes we have to split the port, subdivide the port into small segments. If my electric field is very strong on the port edge, then this might happen, So the freezing field might couple from one port to another port. And this will create unintentional crosstalk, unintentional common mode, and unintentional imbalance, right? So the displacement current starts flowing from one port to other port. In reality, it should be flowing back from the signal plane, or the return plane, right? And so if my port is really small, as you can see here, the electric field will be very strong. But once the port becomes bigger and bigger, the electric field starts decaying. Now it's really, like sometimes really challenging to know what is the adequate or the optimal port size. Right, so as I told, if my port is small, I have a lot of problems. If my port is bigger, then also it comes with its own problem. So the lot of higher order modes, the spurious modes get generated. So let's say my TEM mode is a fundamental or my intentional mode. But sometimes I might get higher order modes in my bandwidth. For example, this is one example I have shown here. So we have a lot of TE10, TE01, and TE11 modes. It might come in my frequency of interest. Let's say my mode conversion spec is up to 300 megahertz. If these modes are coming away from the 300 megahertz, it might not be a problem for me. But if my port size is very small, the cutoff frequency changes. So it might come in my bandwidth. It might show that, unwanted ripples, unwanted mode conversions, all these things. Let me go back. Yeah. And this is, as I told, another problem. So especially this is very much relevant to our 10BASE-T, because we are talking about, even if you see a lot of demos on 10BASE-T in the booth, if you just see, you'll see there will be a PCBs, there will be a connector having a lot of pins. Even though they are using only few pins, but you will see a very bulk connector, right? And if you want to simulate those kind of connectors, there will be a lot of pins. So it really boils down to, how my electromagnetic waves are behaving, what kind of port-to-port couplings are there, because I don't want something that is coming from the port, right? So all these things really matters. And yes, there is an industry challenge actually in, doing this kind of ports. So I told that non-idle port is not suitable for this kind of off-the-shelf connector. Sorry, idle port, we have to use a non-idle port. Now, non-idle port also comes with its own challenges. Because, at the end of the day, I don't want to spend 2-3 months on doing R&D only on how to create a correct port, right? Because I have to do other good stuff on making the connector good, making sure my system works. So what is the answer then? The answer would be, we need an engineer connector with a reference impedance known to us. So if you have those kind of connectors, then it's easy to simulate, easy to know my budget, and it's also easy to control the untwist if you have an engineering connector. Yes, if we are talking about the frequencies at megahertz range, because of the wavelength and all those physics of electromagnetics, the interconnect or the connector might look very small. It might not affect my budget. But if you see from a bigger picture, interconnect is as critical as cable, because we have to control the cable and we have to make sure simulation is correct. So I just want to summarize my key takeaways. So interconnect is transparent at 700 picoseconds, especially in the context of 10BASE-T1S, and cable untwisting effect dominates. It really dominates the 10BASE-T1S link segment, and dual wire at plug, especially with double soldering, has a lot of advantages compared to sorting on the PCB, especially in the context of multi-drop kind of application. And there is a industry challenge on the way we simulate using a non-idle port for this kind of off-the-shelf multi-way connector, right? And so now we know that 10-base-T1S is very sensitive to the way we handle the cable. So really the question would be, like, can we really leverage the CAN-like wiring in 10-base-T1S? So this is an open question we have put to everyone. So everybody can think, and we are there in the booth. You can come visit us and we can have a discussion. So we have a demonstration on some of these ideas where we are showing how we are controlling the untwist, how the even though the multi-node fails, how the communication link is established, especially for a mission critical applications like ADAS and all. So thank you for your time. So please feel free to ask any questions. Yeah.
Thank you for the presentation. So any questions?
Hi, I'm John from Intrepid. And first of all, thank you. This is typically a topic that I really have a tough time comprehending, and I followed pretty much everything from start to finish. So I really appreciate the time you put into the presentation. The question I have is, so you're proposing soldering wires at the connector as opposed to crimping. Is that something that's been done before in other automotive applications? And are there any trade-offs? Is it in terms of robustness, or in the environment, are there other considerations that need, or problems that need to be solved?
Yeah, so in the context of 10-base-T1S, double soldering is very unique. And if I'm not wrong, I don't think we have any existing cable connector system that has double soldering kind of application in the context of 10-base-T1S. It has some advantages compared to double crimping, right? The stub is less. Double crimping itself comes with its own challenges, right? It's not a proven one. Having those double crimping is really challenging. And in terms of the complexity, and also, I mean, we are still investigating and doing, like we have a planned testing coming up in the few months. So we'll be doing a lot of testing and all. Right now, it's still we are working on some of the testing, some of the ideas and all. Yeah, yeah.
Oh, okay. Okay. Yeah. Okay. Yeah, we could talk later.
Other questions?
Hello. Yeah. So for the untwist study you did in the simulation, how much deviation do you expect between simulation measured data, and do you plan to validate the study in the future?
Yeah, so that's a good question, right? Now, so this study we did considering only the connector and the cable, right? But now the next work which we are planning to do is to replicate the way we do the measurement, because especially in this kind of UTP systems, the differential has a return path for P and N. But if you see the common current, it don't have a return path because we don't have a shield. So it flows either through the table, the copper table that we'll be using in the test bench, or it can take, if we have a multi-way connector, then it can take return as adjacent pin. So we expect a very good correlation, but in the next study, what we are going to do is we will be going to replicate exactly what we'll be doing in the test. Whether it's a drum or whether it's a copper table, so we'll be designing a copper table, maintaining the same distance, because in reality, so there will be a bench, right? So let's say I have a distance of 10 mm from the on the unshielded cable to the copper. So this will be my return for the common mode, which will be typically very high. If you see a common mode impedance in a shielded system, it's normally 25 ohm. But in this kind of system, it's really high, like 200, 250. So we have to make sure we are replicating exactly same what we'll be doing in the test. And if you do that, and if you follow whatever we have told in terms of ports and all, yeah, we expect a very good correlation, like 90 to 95% correlation, especially for return loss and mode conversion.
Okay, thanks. I have another question about the waveport that you mentioned. It can detect higher order modes other than the TEM. So is using a discrete or lump port could be a solution to avoid the other modes to propagate?
Exactly, it can be a solution because lump port doesn't support higher order modes only. Lump port has only TM modes, but the problem with lump port is it needs a reference impedance. For an engineering connector, that is a solution. Because I know my impedance, in lump port I can define my reference as 50 or 100. But if I have an off-the-shelf connector, I don't know my reference impedance. In that case, lump port might not be the best choice to do. Because I don't know the impedance of my system, right? Yeah.
Otherwise, you have to add PCB and SMA to simulate. all of those
Yeah,
things.
yeah. Add two PCBs, SMA, but it really complicates the simulation. Yeah.
Okay, thanks.
Okay, so thank you.
Thanks. Yeah.
So we'll take a break of 30 minutes, and after the session of SDV by SDN will be animated by my colleague Reda Benada. Thank you.